we are looking here at two cylinders connected at V. So we have AB that is 10 inches long, and we have BC that is 12 inches long. And we are given that the area of AB is equal to 0.1 square inch. The area of BC is equal to 0.15 square inch. They both have the same modulus of elasticity E of 10 million psi. And the two cylinders are subject to a force applied at V of 1 kip. We are asked to find the wall reactions and we have one wall to the left here, A. We have another wall to the right, C. And the gap between the part and C, this distance, is equal to 0.002 inches. We also want to find the internal forces. And we want to find the displacement of B. So first, let's make sure we understand the problem. And this is always a very important step to understand what's going on. So what's happening here is we have like these two cylinders. They are fixed to the left, but they are allowed to move until they hit the wall a distance of 0.002 inch. They are subject to this force of 1 kip pushing them from the left to the right. So how do we expect these to behave? Because we're asked to find the internal forces. Very good. So the suggestion here, if they are pushed towards the wall, and if they hit the wall, then the wall is going to push back. And if it pushes back, it puts BC for sure in compression. Is AB in tension or in compression? And is in tension. If B is going to move to the right, then AB must be in tension. And when we are mentioning here tension and compression, we are thinking of these as clearly axially loaded members but we never mention bending, we never mention torsion. So these are behaving, each of them, like a two-force member that is either in tension or in compression. Is axially loaded members. So when we are thinking here internal forces, based on our analysis of what's going to happen, we are probably looking at, or we are looking at normal forces. No moment, no torques. So if this is pushing 1K, we expect this wall to pull back. And if it hits C, we expect another push to the left from C. It is best to show that on a free body diagram. So if I look at a free body diagram, A, B, and C, I would say for sure that as a result of this 1K or 1,000 pounds applied at B, I do expect a reaction here, RA. And there is an if C hits the wall, then the wall is going to respond back and push RC. But then I'm going to leave this with a question mark. So the first question mark here would be, would C hit the wall to the right? How can we answer this question? Excellent, excellent. So the suggestion here, if I want to figure out whether it hits the wall or not, I start by thinking of this part as if there is no wall and see how much is going to move to the right. How do we do that? How do we see how much it moves? If there is no wall, would BC deform? Would BC undergo any deformation if there is no wall? No. So BC is going to move to the right freely if there is no wall. So then what governs how far C is going to move? And not exactly the reaction at A, but of course the fact that it is being held at A. So really what's going to govern how far it moves is how much AB is going to stretch. So can we find how much AB is going to stretch? That becomes our question. So in order to answer this question, I would say I need to find delta AB. Are you all following? If delta AB is greater than 0.002, then it will hit the wall. So how do I find delta AB? Elongation in axially loaded member. So wouldn't that be N, the normal force in AB, multiplied by the length of AB, divided by the modulus of elasticity, divided by the area, NL over EA? Correct? So next here, I know the length of AB, I know E, I know the area. But what is the normal force in AB? If there is no wall and I cut here, or even if there is a wall and I cut here and draw a free body diagram for AB. So if we cut here and I draw that part, I will find that I have here RA, and here I'm exposing that normal force AB. So then NAB must be equal to RA. If there is no wall at C, so if there is no wall at C, then RA must be equal to 1,000 pounds, because that's the only thing that would be resisting the 1,000 pounds. If RA is equal to 1,000, then NAB would be equal to 1,000. So now I can substitute in this equation to find that delta AB. So delta AB is equal to this NAB of 1000 multiplied by the length of AB, which is 10, divided by E, which is 10 times 10 to the power 6, divided by the area, which we have here a 0.1. So when I do the numbers, I get a 0.01 inch. What am I going to do with this number? What is it that we're trying to do? Very good. Compare it to the gap. So this is greater than 0.002 inches. So we can conclude from that C will hit the wall. If I come to this conclusion, then I'm going back to my free body diagram. And now I know I have an RA and an RC. How are we going to handle these? So using the free body diagram with both RA and RC, we can do some of the forces in the X direction equal to 0. And I will be able to write here that minus RA plus 1000 minus RC is equal to 0. Right? This is positive X. And I can call this equation 1. How many unknowns do we have in equation 1? 2. Right? So this is not sufficient. So how would I solve the problem? I need an additional equation. Where would this additional equation come from? So need an additional equation. This is what you did in solid mechanics, ES202. We used compatibility. So what does compatibility tell you? I have the part A, AB, that is going to be in tension. So we know that NAB, the normal force in AB, based on this free body diagram, is always going to be equal to RA, correct? If I also draw another free body diagram, if I cut here, and draw another free body diagram to the right piece. So I'm going to have this here. And I'm cutting. So I'm exposing a normal force. And this normal force, I'm expecting RC to be pushing in this direction. And this normal force then here, I know is going to be compression. So I can show it as compression. So I can write here that this is NBC, and NBC is equal to minus, because it's compression, RC. Okay, so now I can write the internal forces in terms of RA and RC. But how is this going to help me with compatibility? If we look at ABC, they have to stay connected at B. How would this happen? This can only happen if the elongation in AB is equal to the compression of BC. And we call that a compatibility condition. We can use it to write a compatibility equation. Can you please repeat? No, you are correct, because I didn't say that very accurately. Point B needs to be at all times on AB and BC. And what I said would only be correct if there was no gap. But because there is a gap, a better way to say that when AB stretch and BC compress, the total deformation or the total elongation can only be 0.002, correct? So yes, this is the better way to say it. So my compatibility is delta total is going to be equal to delta AB, which is positive, we know that, plus delta BC, which is negative. When these two are added together, they can only be equal to 0.002. Does that make more sense now? So delta AB, this is equal to NAB times LAB divided by E divided by the area of AB plus NBC times LBC divided by E divided by the area of BC, and these two combined must be equal to 0.002. Now a question here, I already found delta AB. Is this the one I should plug here? No, why not? When I calculated the delta AB here, we were assuming that the part is not hitting the wall if there is no wall at C. But now we're looking at it with the wall at C. So the normal force is not going to be 1,000. Correct? It's going to be RA. And RA plus RC are going to be equal to 1,000. So now the wall at C is contributing. So what I can do here is I can use that NAB is equal to RA. And I'll come here to this equation and say RA multiplied by the length of AB, which is 10 inches, divided by 10 times 10 to the power 6, divided by the area, which is 0.1, plus NBC is a minus RC, multiplied by the length of BC, which is 12 inches, divided by E, which is 10 times 10 to the power 6, divided by the area of BC, which is given as 0.15. These must be equal to 0.002 inches. I will call this equation 2. You see here I have equation 1 and equation 2, and I only have two unknowns, RA and RC. From 1 and 2, we can find that RA is equal to 555.56 pounds, and RC is equal to 444.44 pounds. And clearly, when you add these two together, you get the 1,000. Is this better? So this is the first thing we were asked to find, the wall reactions. Next, the internal forces. If I have RA, I have NAB. So I can come here and report that the normal force in AB is equal to 555.56 in tension. If I know RC, I can find NBC. So NBC is equal to RC, 444.44. And yes, we have a negative sign here because that means it is in compression. So here are the internal forces. And the last thing we were asked to find is displacement at B. So how would I find the displacement at B? I have the wall to the left, which is my reference frame. So if I can find now the elongation of AB, that would give me the displacement of B. Okay. So we can look here at finding delta B is equal to delta AB is equal to NAB times LAB divided by E divided by the area of AB. Okay. So when I substitute here, I will have this 555.56 multiplied by 10 divided by 10 times 10 to the power 6 divided by 0.1. This is equal to 0.00555 inches. So we can report that delta B is going to be 0.00555 inches. So we have found all what we were asked to find. Just if you take a quick look, if this is 0.0055, so that tells us that point B is going to move more than the gap, which proves the case that BC is going to be in compression and AB is going to be in tension. Does that make sense? What did we call these type of problems in solids? When equations of equilibrium are not sufficient and we need compatibility equation. Remember? No, superposition was to look at different effects and add them, right? But we call these when the unknowns are more than the equations of equilibrium, we call them indeterminate problems. So this is the problem we just solved. And the reason I picked this one, because I want to see you show you the advantage of the finite element method to solve both determinate and indeterminate problems without having to write compatibility equations. So now I want to solve the very same problem using finite element method. Okay. So here is my problem, and we want to use the finite element method to solve the very same problem. The very first step would be what? I think last time we wrote some steps for the finite element method, or we did not. Here are the steps that we discussed last week. Number one is to write the element stiffness matrices for element 1 and element 2, or however elements we have. We label each row and column of the element stiffness matrices, which is corresponding degrees of freedom. We expand the case to the size of the global stiffness matrix K, and then we add them to assemble or to put together this global stiffness matrix K. And then we apply the boundary conditions to solve for the unknowns. And then we can use the element stiffness equations to solve for the internal forces. So these are the steps we are going to apply today. And I think you all have these in your notes. We wrote like 7 steps. So I want you to pay attention as of how we're going to apply these steps to solve this problem. So when I look at this problem, the first step is to discretize, to take this continuous system and make a mesh. So looking at it, each piece, like AB and BC, each of them is like a bar or a string, right? So I can model these as 2 bar elements. One is 10-inch and the other is 12 inches. So if this is like A, B, C, I'm going to give it the numbers 1, 2, and 3. I'm going to call this element 1, and I'm going to call this element 2. So element 1 is between 1 and 2, 2 nodes, and element 2 is between 2 and 3. Now I'm going to start by writing the element stiffness matrices. So for element 1, my K1 is equal to EA over L, which is equal to E is 10 times 10 to the power 6. The area is 0.1, and the length is 10 inches. So I get here a 10 to the power 5 pound per inch. For element 2, K2 is equal to E, the area of BC. So this was the area of AB, of course, length of AB. Here I have the length of BC. So this is equal again to 10 times 10 to the power 6 multiplied by the area, which is 0.15, divided by the length, which is 12. This is equal to 1.25 times 10 to the power 5 pound per inch. So when I want to write the stiffness matrices, I have this K1 matrix, which is a 2 by 2. This is going to be equal to 10 to the power 5 common factor. And then I have a 1 minus 1 minus 1 and 1, as we have learned. Next, I'm going to write K2, a 2 by 2 also. And now I have this 1.25 times 10 to the power 5. And here I have a 1 minus 1 minus 1 and 1. I want to mark my element stiffness matrices, rows and columns, to their corresponding degrees of freedom. I hope that you're all paying attention and try to avoid distraction using any electronic gadgets as we learn how to assemble the global stiffness matrix. So in element 1, the matrix here connects between A and B, or 1 and 2. So the first row corresponds to the first degree of freedom. So I can say that this refers to U1 and the second is U2. The first column likewise would be labeled U1 and U2. As for element 2, extending between B and C, or between node 2 and node 3, would correspond to a U2 and a U3. Likewise for the column U2 and U3. So we mark the rows and columns with respect to the corresponding degrees of freedom. Now it is time to assemble the global stiffness equation. Matrix. Assemble the global stiffness matrix. That's the uppercase K. And we said that this K, in this case, we have 3 degrees of freedom, right? Namely, U1, U2, and U3. So because I have 3 degrees of freedom, this K is going to be a 3 by 3 matrix. And it's going to be equal to the sigma from I equal 1 to 2, because I have 2 elements, of the K I's. And we want to make sure that when we do the summation, every element is going into its corresponding location. So now I'm going to write this K as equal to so here I'm going to have U1, U2, and U3, U1, U2, and U3. And I'm going to do the summation. So for element 1, I'm going to take the 10 to the power 5 as a common factor. And I'm going to come here and put a 1, a minus 1, a minus 1, and the 1. You see where this is coming from? U1, U2, U1, U2, U1, U2, U1, U2. Now, when I look at K2, it needs to go in U2, U3 area. So I'm going to come here and put a plus 1.25 times 10 to the power 5, a minus 1, a minus 1, and the 1. Everywhere else that I don't have an entry, I'm simply going to put a 0. So if we look carefully, here is K2, and here is K1. And this is how we superimpose them or add them together to come up with this stiffness matrix K. I'm sorry, you're referring to these entries? Yeah, they're 1.25, sorry. Yeah. Thank you for catching that. Now, once I have my global stiffness matrix K, we can solve the stiffness equations using boundary conditions. So first, what are the boundary conditions we have for this problem? When I compare these two together, what are my boundary conditions? I have a reaction, I rather have a support. And the support is preventing A from moving to the left or to the right. So I can come here and say, as part of my boundary conditions, U1 must be equal to 0. Is that the only boundary condition? If you look at C, the wall can move or is gonna move 0.002 inch. So I can come here and say, oh, this is U3. So U3 is equal to 0.002 inches. Correct? So what are my global stiffness equations? They can be written as F equals to K times D. Right. But what is F? F, these are the external forces. What are my external forces? I didn't show it on this diagram, but we can clearly show that there is an RA, there is going to be an RC, and at B, we have this 1,000 pounds. So we can write F as RA with a negative sign, because this is my positive X direction. I have a 1,000 pounds positive and a minus RC at node 3. So this is my F is equal to my K so we have this 3 by 3 multiplied by U1, U2, and U3. But now we know that U1 is going to be a 0. Right? Now, if U1 is a 0, I can cross the first column or delete the first column corresponding to U1 because they're multiplied by 0. And also, if we know U1, and we want to solve now for U, and we know U3 too, by the way, but I can also cross the first row and focus on the second two, right? On the second two here, we're going to have a plus 1.25, a minus 1.25, a minus 1.25. Sorry, this is 2.25. And here we have a 1.25. So I can write two equations. 1,000 is equal to 2.25 times 10 to the power 5 U2 minus 1.25 times 10 to the power 5. Now U3 is 0.002. From this equation right here, I can solve for U2. And we'll find that U2 is equal to 0.0055556 inches. Now, if I have U2 and I know U3, I can solve for RC. And I'll find that RC is equal to 444.44 pounds. Now, I have U2, U3, and I know U1 is a 0. I can use the first line, which had a 1 here and a minus 1 here. So I can solve for RA, which is going to be equal to minus 10 to the power 5 multiplied by U2 actually this is a minus RA, right? So this is equal to minus 555.56. Therefore, RA is equal to a positive 555.56. When I say positive, the direction is as we showed it here. So this way I was able to solve for the displacement at B and the wall reaction. UB or delta B, displacement at B is equal to U2 is equal to that 0.05556. The only thing that is remaining now are the internal forces. The internal forces are the same as the element forces. So I can come here and say, for the element forces, using element stiffness equations. What are the element stiffness equations? F is equal to lowercase k, and this is lowercase f, multiplied by d. This is a 2 by 1, this is a 2 by 2, and this is a 2 by 1. So for element 1, I have F1 applied to element 1 and F2 applied to element 1 are equal to 10 to the power 5 times 1 minus 1 minus 1 and 1 multiplied by D, which is U1 is a 0 and U2 is this 0.005556. And by the way, if I show element 1 extending here between 1 and 2, this is X. So this is F11, and here this would be F21. When I solve this, we'll find that F11 is equal to a minus 555.56 pounds. And F21 is equal to a plus 555.56 pounds. Isn't this is a two-force member? Shouldn't the two be the same, either tension or compression? Yes. I'm getting here one negative and one positive because if you look at the sign convention, when F11 is negative, that means tension. When F21 is positive, it also means tension. You all see that clearly? So I can come here and report that the normal force in AB is 555.56 pounds in tension. Next, we can go to element 2. And again, we can show element 2 as extending between 2 and 3. The element forces, this is my positive X direction. So here I would have an F2 as it applies to element 2. This was 1. And an F3, 2 at node 3. So we can write here F2, 2 and F3, 2. These are equal to 1.25 times 10 to the power 5 1 minus 1 minus 1, 1, multiplied by U2, which is 0.0055556, and a U3 of 0.002. Both of them are positive. Okay. When we do the numbers, I will get here F22 to be equal to a plus 444.44 pounds, and F32 is equal to a minus 444.44 pounds. Again, if this is positive, this is negative, this means that BC is in compression, and I can report that NBC is equal to, or has the internal force is 4.44 pounds in compression, which are the same answers we got when we solved the problem using equations of equilibrium and compatibility. So here, if we look at these 2 pages, we were able to solve the same problem using the finite element method by hand. Again, this is simple 2-bar elements connected together. And yes, we can do 3 and 4 as you're going to do in the homework by hand. But of course, if we have tens or hundreds, it's going to require more number manipulations. And this is where a computer program will come in handy.